Alright, so today we're going to be looking at rational exponents. So I'm going to start off first with a with an exponent of 1 over n. So I'm going to introduce the fractional exponent. Okay, so when we're looking at the fractional exponent, I'm going to look at it from the standpoint of using our exponent laws. So let's say I had something like this, right? 3 with an exponent of 1/2 times 3 with an exponent of 1/2. Okay, our exponent laws tell us that because the base is the same, that we could write this as 3 with an exponent of 1/2 plus that other exponent of 1/2. And that would then become 3 with an exponent of 1, because 1/2 plus 1/2 is 1. Okay. Now I also want you to remember back to when we were working with radicals, right? So I also had the same thing where I said the square root of 3 times the square root of 3. I could write that as the square root of 3 times 3, which was then the square root of 3 squared, which was just 3. So 3 with an exponent of 1/2 times 3 with an exponent of 1/2 is 3, and so is the square root of 3 times the square root of 3. So really, these two things must then be equal to one another. Those are the exact same factor. Okay, so they're the exact same thing. And this holds true even if we have a different index. Okay, so it doesn't just work with a square root. I could do this with something like the fourth root. So let's say I had the fourth root of 5 times the fourth root of 5 times the fourth root of 5. And I'm sorry that that second one looks so terrible. Okay, if I had the fourth root of 5 multiplying itself 4 times, that would then become the fourth root of 5 times 5 times 5 times 5. And I've got 4 5's under the radical sign, so that would be the fourth root of 5 with an exponent of 4, and that would really just be 5. Well, the same thing holds true if I have an exponent of 1/4. If I go 5 with an exponent of 1/4, and I multiply it by itself, and I've got 4 of them, my exponent laws would tell me to add all of those 1/4s together. Right? I've got 4 of them all added together, and that would really just be 5 with an exponent of 1. So again, using that same argument, the fourth root of 5 is equal to 5 with an exponent of 1/4. Okay? So in general, if you've got a fractional exponent, a with an exponent of 1 over n, that's the same thing as the nth root of a. Okay? Alright, now, what if I actually have something in my numerator, though, that isn't 1? What would happen here? Okay, so let's look at something maybe like 3 with an exponent of 3/2 times 3 with an exponent of 3/2. Okay, so my exponent law, again, would tell me to add them together. So I add them together. 3/2 plus 3 more halves is going to give me 3 in total, 6/2, right? And 6 divided by 2 would be 3. So I get 3 with an exponent of 3. Well, the same thing would happen if I took the square root of 3 cubed and I multiplied by the square root of 3 cubed. Okay, now I'm taking the square root because when you look back, my denominator in my exponent was a 2, and we just talked about the denominator being the same as the index in our radical. Okay, so this one here, I would have the square root of 3 cubed times 3 cubed, and that gives me the square root of 3 exponent 6, and 3 exponent 6, take the square root of that, we get 3 exponent 3. Okay, so 3 with an exponent of 3/2 ended up being equal to the square root of 3 with an exponent of 3. Okay, those are the same thing. And again, it works with other indexes as well. Okay, so it's not just a square root, it would work with something else. So I'll kind of go back to that same example we had before. What if I pick that we'll say the denominator here is 4. So that would mean I'm looking at the fourth root, right? Okay, so if I was to use my exponent laws here, it would tell me to go 5 with that exponent of 3 over 4, and I'm going to add all of those 3 over 4's together. And when we add all of those 3 over 4's together, we would have 12 over 4, and that's the same thing as 5 with an exponent of 3. Okay, well, it's the same as if I took the fourth root of 5 cubed times the fourth root of 5 cubed times the fourth root of 5 cubed, right? So if I've got 4 of those things here, they can all sit under the 1 radical symbol, or sorry, radical sign, not plus, it's times 5 cubed times 5 cubed. And so I've got the fourth root of 5 with an exponent of 12, and the fourth root of that is going to be 5 with an exponent of 3. So again, I've got 5 with an exponent of 3 over 4 is equal to the fourth root of 5 cubed. Okay, so really what that gives us is, if we look in general terms, a with an exponent of m over n is going to equal the nth root of a with an exponent of m. Okay, so it's a quick way that I can change from exponential form back into radical form. Okay, now with that, I'm going to show you there's 2 different ways we can work with that one. Okay, so for example, what if I wanted to evaluate something like this? So I've got 16 to an exponent of 3 over 4. Now I've got 2 choices on how I do it. One I think is a little bit more difficult because you need your calculator to help you, and the other one we can do this without. So I'm going to show you the hard way first. Okay, so option number 1, if I've got 16 to an exponent of 3 over 4, I can write that as the fourth root of 16 cubed. Okay, well, 16 cubed is 4,096. Now I didn't know that. I had to go 16 times 16 times 16 to double check because I wasn't sure. Okay, and I definitely don't know the fourth root of this off the top of my head, so I had to type that into my calculator. I had to find the fourth root of 4,096, and it ends up being 8. Okay, now that's, not unmanageable, but I can do this exact same thing without using the calculator at all. I'm just going to change the way I look at it. Okay, so what I'm going to do is, instead here, I'm going to think of 16 and 3 over 4 as the exponent. I'm going to break this apart. I'm going to think of it as 16 with an exponent of 1 over 4 and use my exponent law to put my other exponent outside, right? Because if I've already got something to an exponent and then I have another exponent outside the brackets, I would simply multiply them. 1/4 times 3 is 3/4. So I still have the same expression. But what this allows me to do is it allows me to take the fourth root of 16, which is something that I know off the top of my head. The fourth root of 16 is 2, and then 2 cubed is 8. Okay, so I'm allowed to work with this in whatever order I like. So option 1, the order that we went with that was we went 16 cubed first, and then we took the fourth root after. And that makes it more difficult for us to actually solve it without the use of a calculator. So option number 2 is great. So if you can, take the root before you do anything else with it, okay, before raising it to another exponent. Okay, all right, let's look at what happens now with with our negative, right? Because our fractions can be both positive and negative. Okay, so I'm just going to show you. Let's say I had something like 27 with an exponent of 2/3 times 27 with an exponent of negative 2/3. Okay, if I was to use my exponent laws, this would become 27 with an exponent of 2/3, and then I'm going to add my second exponent. So I'm going to add negative 2/3. And 2/3 plus negative 2/3 is 0. And so I just get 1, right? That's just using the exponent laws and adding those two exponents together. Okay, so if I was to break that down a little bit more, 27 with an exponent of 2/3 is the same thing as the cubed root of 27 squared. And the cubed root of 27 is 3, and 3 squared is 9. So if that first factor here is equal to 9, 9 times what gives me 1, right? Because when I multiplied these two things together, I got 1. So the second thing is going to have to be 1 over 9, right? 27 with an exponent of negative 2/3 is going to have to be 1 over 9, which is really just the reciprocal of what we saw over here, right? It's the reciprocal of that. Okay, so let's work through it to actually prove that it works that way. Okay, but we know what we should be getting. So let's say I had 27 with an exponent of negative 2/3. Okay, I'm going to split this apart. Okay, I'm going to write it as negative, or I'm going to write as 27 with an exponent of 2/3, and I'm going to put that negative 1 outside. Okay, so I'm just using my exponent laws to pull that negative apart. Well, I know that this is then the cubed root of 27, and it's going to be squared, and then it's got that exponent of negative 1. I know the square, or the cubed root of 27 is 3, and 3 squared gives me 9, and then I have 9 to an exponent of negative 1, which is 1 over 9. If you really wanted, you could have done the negative first, and that makes it 1 over 27 to an exponent of 2 over 3, and well, we know 27 with an exponent of 2/3 is 9, so I get 1 over 9. Okay, so really what's happening with that negative, when I had negative m over n, was it ended up being the reciprocal, just like it was before. Okay, so it's whatever we would get normally, but just the reciprocal of it. Okay, so this gives us two new exponent laws that I'll leave up here for you right on the last slide. Okay, and it's basically just saying, if you look here, it says a with an exponent of m over n is equal to the nth root of a with an exponent of m. So really, the key thing to remember here is the denominator is your index, and then the numerator is still just the exponent attached to the base. Okay? Now, your choice as to how you want to interpret it, but I think everything in this column is way simpler to work with because you're taking the root of the number first, and so that allows you most of the time to work without a calculator because you're taking the root of something before it gets too big. If you raise it to its exponent first and then try to take the nth root of it, chances are you're going to need the calculator almost every single time. So I like to do that because generally I know the square roots, I know cubed roots, fourth roots, I know them when they're smaller rather than when they're bigger. And to avoid using the calculator, I'm going to pick remembering it like this because I think it's a little bit easier to work with. Alright, that's working with rational exponents. Next video we'll have some more examples on how to do some of these calculations.